V. Q is doubled. All right, what have we done to the electric field? Is this a simple problem? We've already cut the electric field in half? Okay. Let me add, just to make it clear. This is the total electric field, which should be the default. I mean, if I specifically want the electric field from the plates, I would need to specify that. Okay, so what happened to the electric field when I added the dielectric?
Stayed the same.
Why?
Because the area didn't change, the distance didn't change, just the capacitance was just doubled. Everything else is fixed, right?
Everything, we haven't changed anything else.
Right, that's why it hasn't been cut in half.
I don't think it's the best reason
Okay.
for, wait, you said it was cut in half?
It's
Or
not.
it's not?
Not yet, no, it's not cut in half. So what you're looking for with the answer is, I need to pick something that doubles as well as cut in half the electric.
Yeah, doubles the charge. We've already doubled the charge, but
Okay, so
the question on the floor is, when we did this, what happened to the electric field?
Didn't do anything to it.
Okay, and your reasoning again, or someone else wanna come in?
I don't think my reasoning is correct, so,
But you are correct, the total electric field is the same.
okay.
The question is, what is the evidence for that? And it's possible, I just didn't follow what you were saying, and it's possible you weren't absolutely spot on, I'm not sure.
Okay.
If the electric field total is calculated with delta V over D, we haven't changed either of those components.
And that's it.
Oh,
Well, from right here. Delta V is fixed because it's still hooked to the battery. D hasn't changed because we didn't say we changed that. So since that ratio is the same, that's the same. So the total electric field hasn't changed. So now I need to cut the electric field in half. How do we do that? Because I still want my charge to stay doubled. First of all, how can I make sure that my charge, we've got the charge doubled, how can I make sure that's not gonna change?
Disconnect?
Yeah, so then disconnect. So now Q is fixed. So now, how do I change the electric field? Or maybe it's not possible. And I always threw that in there because years ago I was given a problem like this, and I said basically how to double this and cut this in half, et cetera, et cetera. And I made a careless error when I was writing the problem, and one of the problems was impossible. So I always offer the possibility that if it's impossible, show why. Yes?
Could we double the distance, which would then, no.
If we double the distance, and I'm assuming if we double the distance, we have a dielectric in there, if we double the distance, the dielectric is just going to magically expand to fill whatever the space is. I'm not gonna have half dielectric and half air, unless you wanna go that route. Right now, let's just keep it simple. Assume the dielectric will fill whatever the space is. So if we change the distance, we'll change the capacitance. My charge stays the same, So if charge stays the same and capacitance changes, my voltage is gonna change. If my voltage changes with the distance change, does that? I'm beginning to wonder if it is possible. So manipulating, because it's parallel plate capacitor, I can do that. I'm just gonna drop the absolute value marks for ease of notation. Let's see, I know that E is equal to sigma over epsilon. Sigma, oh, okay, is equal to, that is the total charge over the area. So that's Q over A epsilon, which is Q over A kappa epsilon sub naught. It is possible. Because we know that Q is fixed. What would we have to do to the area?
It would still have to be, I think, doubled, because essentially it's the bottom to the top of the ball.
Okay.
Just right
So
here.
if we double the area, then, well, Q hasn't changed because we disconnected. If we double the area, the total electric field would be cut in half. We could also change the dielectric for one with a dielectric constant of 4. And questions?
Is that the only two ways from this point to do that?
Excuse me?
Is that the only two ways from this point to do that?
Given that equation, let's see, says we can't change the charge. There might be another slicker way of doing it. That's what's coming to me at the moment.
Would you be doubling the area by increasing the plate size?
Yes. And you will not double the area if you make it a 20 by 20, just in case you forgot. That will make it 4 times bigger. So I guess the plates would expand by square root of 2. Anyway. The fun that's in these problems. Notice also, we didn't actually have to calculate what the charge was. We didn't have to actually calculate what the electric field was in order to solve the problem. I've done this before where I said, just assume the initial charge on the plate is Q sub 0 and the initial electric field is E sub 0. And then you can work out the rest of the problem in terms of those. But most students in the past like numbers. So they put in the numbers as opposed to keep it in simpler terms. Any questions before we talk about multiple capacitors? I shouldn't have said that because that gets you so excited for the next bit that you think, oh, I'm not gonna ask any questions because I just want to get to multiple capacitors as soon as possible. Yeah, I know you guys know what I'm talking about. I'm gonna take take the battery here, attach it to a parallel plate capacitor. That should not be anything bizarre to you. Done that on the board several times. This is some potential difference, this is some capacitance. I'm now gonna take my connection here, and I'm gonna change it. I keep that there, got my capacitor, and this time I'm going to split the wire so it touches in two spots. Does that change the capacitance or amount of charge? Does it change anything of any note other than the wire? I took the ends of the wire and I spread it apart. Okay, so nothing has changed. Now what I'm going to do is I am going to easier to draw it. All right. I'm going to take this, I got my wire split, and I'm going to take my capacitor, it's supposed to be the same distance between them in each case, and I'm just going to put a small little gap in between. So basically putting a small little gap in the plate. So I still have charge coming up to the plates. The only difference between this and this is instead of having to connect it, there's just a small little gap there. Can I store just as much charge on this as I did on that? That is correct. So my total capacitance here is the same as my total capacitance here. For the same voltage, I can store just as much charge here as I could here. Except this is two capacitors, and that's one capacitor. So whatever the capacitance of this, the total capacitance of this, is the same as the total capacitance of that. And so I'm going to call that C1 and C2. I know that my capacitance, with parallel plates, I have kappa epsilon naught A over D. In my area, I can break into kappa epsilon sub naught over D, A1 plus A2. So we'll just call this as an area of A1, that's an area of A2. Which is just kappa epsilon sub naught A1 over D plus kappa epsilon naught A1 A2 over D, which is just capacitance 1 plus capacitance 2. The takeaway from this for capacitors in parallel, the equivalent capacitance CEQ equals C1 plus C2 plus however many capacitors I have in parallel. Right. So part of this is what is parallel. So imagine I've got charges flowing from the negative side of the battery, which they want to do. I get a negative charge coming out of here, negative charge cruises up here, gets to this point, and it splits. Or over here, negative charge coming in, the electrons coming in, and it's going to go one path or the other. And then they're going to join up again. So if you think in terms of current, I have current flowing onto the one side, it's going to flow out the other. It doesn't matter which path I take. I know that from Kirchhoff's voltage rule, if this is let's say a 12 volt battery here, I come up here, I get to this point, and then I go across here, I'm going to lose 12 volts going this way. Or I can go 12 volts like this and then lose 12 volts going this way. And then back to where I started. If it is parallel, one, I'm going to have a splitting of the charge flow, or current, And two, objects in parallel have the same potential difference. Because the path doesn't matter. If I go from this point to this point, whichever path I go is gonna have the same potential drop. So parallel objects in parallel have same potential difference. And what is in parallel are basically the paths. That path there and that path there are considered parallel to each other. All right, so let's do a quick and dirty exercise there. Two farad and 3 farad. What is the equivalent capacitance? In unison, be really cool right now. 3, 2, 1.
5.
There we go. Give me the whole thing.
5 volts. Farads.
Farads.
So that's
Yeah, it's just add them up. Let's make it look more difficult. What's the equivalent capacitance?
9 farads. 9 farads.
Yeah. So if you're doing some electronics work and you have this configuration, you could just pull that out, stick in a 9 farad capacitor, and you're good to go. Now here, if you look at this sort of junction right there, that's considered to be a single junction. I could have written this just as easily as I got coming in like that, boom. I got my 2 farad right there. Three farad, 4 farad. Those are the same from a schematic point of view. We assume that the wires are perfect right now. Ideal, superconducting, no resistance. Wires offer nothing but decoration for the most part. And connections. Questions here? I'm now going to take my capacitor. So capacitance C. Now I'm going to separate the plates. And what I want to do is, whatever distance that is right there, I'm going to stick another. I'm just going to create 2 capacitors from that one, where this distance here we call this D1 and this D2, where D1 plus D2 is equal to D. The capacitance here, I know, is kappa epsilon sub naught A over D, which is kappa epsilon sub naught A over D1 plus D2. Let's see. Alright, well, let's think about this though. I've got a capacitor here, hooked to a battery. This is some potential difference of delta V. This going across that way would have some potential difference of negative delta V. If that's 12 volts, it's negative 12 volts going to the right, positive 12 volts going to the left. I'm gonna build up some charge here, Q, and some, negative Q and some charge here, Q. If I stick something in between, I'm gonna have some potential drop across there, some potential drop across there. So it's delta V. So my potential drop here would be delta V1, my potential drop here would be delta V2. I know that delta V1 plus delta V2 has to add up to delta V. I'm ignoring signs. I know that the potential, well, capacitance is Q over delta V, so delta V is equal to Q over C. Doing a different tack than what I was doing right there. So this would be whatever charge I have on the first one over the capacitance of the first one, plus the charge I have on the second one over the capacitance of the second one, is going to be equal to the total charge on the first capacitor over that capacitor. But if I'm building charge up on this, I would develop some charge negative Q there and Q here. Because every time an electron shows up here, it chases one over to here, so this would have a charge of negative Q, this would have a charge of Q. The charge that I have on each of these capacitors is the same. What I'm saying here is that Q1, Q2, and Q are all the same. But if they're all the same, I can divide by it, and what I'm left with is 1 over C1 plus 1 over C2 is 1 over C.